a holiday for most of the world, so I can realize that some people would not be able to join or spend their evening with us, and that's okay. But for those who is here with us today, thank you for joining and thank you for taking the time. So we have myself and Brian McMahon today presenting on the two topics, first of which is the protection lattice of M4 endpoints, and the second one is the role of machine learning in endpoint security. I think both topics are fundamental to understanding how our M4 endpoints solution works and how it's different from what's being offered on the market. And first of all, let us start with the first section, with the protection lattice section. So the protection lattice itself is a combination of security components that work as a part of the security architecture of the M4 endpoints agent. And there are components that work on the agent itself, and as well there are components that work by collecting the intelligence from the AMP cloud. The important part is that those components work together to provide enhanced levels of protection. When we look at the protection lattice for the AMP connector for Windows, we usually try to look at this from the perspective of the time to detection, because obviously the shorter this time is, the better it is for the customer. If we have longer times to detection, it really means more effort for the customer to clean up, more later detection. It means really more time required to remediate, and as a result, more money spent. And that, of course, affects the business. So looking at the capabilities here that we have on the Windows connector, we have capabilities grouped into three buckets. The first bucket is the engines that work against attacks that are trying to target memory vulnerabilities or memory attacks. The second bucket is actually the engines that look for weird or suspicious activities or for bad files that land on the disk of the endpoint. And there are multiple components there, including the AMP Cloud Intelligence, the behavioral analysis that we have with our malicious activity protection engine, and of course the antivirus engine. We have discussed it briefly yesterday, speaking of Tetra for Windows or QEMU for Mac and Linux. Finally, we have a bucket of engines that work for post-compromise detection. Clearly, those are the engines that serve as our final kind of line of detection and defense, and they could be really useful for incident response. Whenever one of the components fails, there is another component that would hopefully be able to pick up the threat that is targeting the endpoint. And in that category, we have the network engine or the device flow correlation. We have the cloud indicators of compromise, as discussed by JC yesterday, that look for suspicious behaviors on the endpoint and report them back to the AMP cloud without actually blocking them. And there is also a component which is named endpoint IOCs, which is mostly used for threat hunting and incident response when you're trying to confirm of presence of certain indicators on your endpoint post-compromise. There is then this thick line underneath those buckets, which is actually called the machine learning or the cognitive intelligence part. The cognitive intelligence part started off as a means of analysis of web telemetry coming from a web proxy. It then got integrated into the M4 endpoints console to serve as the additional efficacy improvement, as additional support for security analysts, which provides more detections for advanced threats that are actually able to circumvent other engines. But as time went, this capability has also emerged, and that's something that we are going to discuss in the second part of this presentation today, because it's now able not only to provide the post-compromise detection, but also it helps and improves the prevention that we have not only across M4 endpoints, but across the entire architecture. So let's start with the in-memory protection first. So the in-memory protection engine, the first one that we have here is our exploit prevention engine. It's important to remember that exploit prevention is an engine which is OEM'd from another vendor. So it's an original equipment manufacturer that provides this component to us, and it's not developed in-house. It's quite important to mention that we as Cisco, we are not allowed to disclose the details of who the OEM vendor is, even if we know those details or how the agreement is made up. The important thing here is that this vendor is actually specialized in the protection against exploits, and they have very solid experience in that area, and that's actually why we have chosen them to be our vendor of choice. The reason they are so successful with what they do is actually quite funny. It is because Microsoft Windows is not as efficient with memory allocations as it could be. So for example, in Windows, if you launch an application, for example, Outlook or Word or some of the other applications, it's always leveraging the assigned memory space. And what this makes up, it makes up a predictable target. If attackers know which memory space is used for that application, they can actually figure out which memory space is used and figure out how can they exploit it. On the other side, what exploit prevention does, it actually completely randomizes the memory allocation to our endpoints and to the processes running on our endpoints, and that makes our endpoints unpredictable targets. So this is something that makes a huge advantage for defenders, because now we don't have defenders chasing unpredictable targets, unpredictable hackers, but we have instead hackers who are trying to chase unpredictable targets, which is always an advantage for us. Let's quickly go through how it works, and I try to explain it by breaking this down into 3 simple steps. The first step, we have a user who is actually loading an application which is on the protection list, and the protection list is something that we'll cover in a few minutes here. It has around 15 applications as of today. So when that application loads, exploit prevention actually injects a small library into the Windows loader. And the Windows loader is a component that is responsible for loading the libraries and the executable itself. So when that happens, that small library of exploit prevention starts randomizing the memory layout of that new application, and it does it on the fly. The user doesn't notice anything. The user doesn't have any significant performance penalty. The application simply starts. Right? What happens in the next step? In the next step, we actually have to tell that application that it now has a different memory allocation. You are not now running from your old memory allocation. You are now running from your new randomized memory structure that is not yet known. So we actually steer that memory structure and the application together so it can function properly. And then the original memory structure that the application had previously is still kept there as a decoy. So whenever an attacker is actually trying to access that decoy memory, or whenever they're trying to access that original memory structure, they're actually not aware of the changes that exploit prevention has done. And as a result, they're hitting the decoy, and that could be reported for investigation to the security analyst to further investigate how the attacker was trying to attack, whether it was a file that was actually trying to exploit an application or a process. As I hope most of you know, there is a white paper that goes much deeper into the details of how this entire thing works. Here is a short link that you can save for yourself, or you can use this white paper for internal purposes as of right now. There is one external white paper that is customer facing that is currently in progress, and we hope to have it pretty soon. Speaking of the processes and applications that are protected by exploit prevention, we have protection for 32-bit and 64-bit processes. 32-bit protection was added first with the connector version 6.0.5, and then after some time we have added the protection for version 6.2.1, which now includes 64-bit protection for the listed applications, like the common ones, Microsoft Excel, Word, PowerPoint, Outlook, Explorer, etc. And that also includes exploit prevention type of protection for some of the system processes, which are listed on the right side here. One important thing that I frequently get asked by customers is, hey, can I actually use my own custom applications and provide the same level of protection for those applications? And the answer right now is no. We have a predefined list here, and we do not currently allow customers to add their own applications. That's something that could probably be figured out later on, but as of right now, that requires some accurate tuning and baselining on the backend to make sure that the engine does not cause any compatibility issues with custom applications. Another important aspect, if a customer is running another solution and maybe they're running something alongside with AMP, and maybe that solution also has the component that does memory modifications. So in that case, a single solution to actually ensure compatibility is to exclude one of these applications from protection. That could be done by opening a tech support case, and that doesn't really present a huge issue there. Speaking from the perspective of the threats that exploit prevention can defeat by itself, we are just speaking about one engine here, just to keep your attention. We have threats in 3 categories that exploit prevention is aimed to address. So these are the high-level categories of exploitation. whenever an attacker is trying to exploit vulnerability, whether a known vulnerability or a zero-day vulnerability, we have the post-exploitation bucket, and that's where we have an attacker who has already exploited vulnerability, and then they're trying to do something useful in the system, like download additional files or inject into other processes which are legitimate, to kind of obfuscate and hide their intentions there. And then there is one more bucket, which is malware. The malware bucket is also quite interesting because it introduces defense for things like adware. So essentially, you can now install a software bundle, and during installation, if exploit prevention determines that this software bundle has a piece of adware, it can actually block that adware component, and then you can proceed with the installation as normal. And this is something that we're going to demonstrate today as well. So speaking of those three buckets, like in exploitation, for example, we have the memory corruption exploits. We have multiple categories that fit here, like the integer overflow or the use after free or the buffer overflow. For example, when we have a program that is attempting to write more data to the buffer and it kind of overflows the buffer, trying to hijack the flow of that application. And speaking of how exploit prevention addresses that, it's quite simple. So if attackers are trying to overflow a buffer of an application, they should know how this application is designed and which kind of memory it's using, or what are the memory addresses that this application is using. And as we have discussed, exploit prevention actually scrambles those addresses, which makes it quite difficult for the attacker to execute attacks of that type. There is, of course, shellcode and code injections, which I assume are more familiar. And as with the case of process following, for example, this is where an attacker is using a simple technique to, first of all, unmap legitimate code from a target process where they're trying to write to. And then what they can do is they can actually inject their malicious code into that process. And what it results in is it results in a process that could potentially be clean, like svchost.exe or explorer.exe, but in reality, in the backend, it's actually running malicious code. So it's a very good way to hide your intentions behind this clean kind of process. As mentioned, there is a lot of details on each of these techniques and a lot of details on how these techniques are defeated, in particular, in the white paper. So please do not miss your chance to have a look at that white paper. And now we have a short demo here. So basically, the demo is demonstrating how you can protect with exploit prevention against the buffer overflow attack. We are using a relatively old exploit here against a very old vulnerability. That's what we had at the moment in the lab against Adobe Reader. And here on the other side, on the attacker side, we are using Kali Linux to simply set up a listener that listens on a particular IP address and port. And basically, this is the steps that you can take. It's that easy. That's quite a powerful combination to show to a customer how easy it can be to exploit. So assigning the port here, assigning the URI path where the exploit is hosted, and then finally clicking on the exploit button. Then once we go, we see that there is the server, the listener has started. Once we go to the side of the victim, let's imagine we went to a particular website and we have downloaded, a random document that could probably look quite legitimate at first. We save the document, and then we open Adobe Reader, and we try to execute that document. And in this case, we see that we have AMP endpoints protection here. It's enabled. So as soon as the attacker tries to execute that document, we have a notification coming from AMP saying that an exploit attempt was prevented. And it tells you exactly on which process it was prevented. So in this case, Adobe Reader. We also see that there is no shell access here on the attacker side. So the attack was not successful in this case. Now if we go back here, and now if we disable our M4 endpoint service, and if we repeat this attack again, let's see what happens. So again, opening Adobe Reader, starting the execution, or pretty much starting that file, and going back to the attacker side, we now see that the attack has succeeded, and the attacker has actually got access to that system. And that's basically where they have access to the system, they have access to the shell, and that's where they would proceed to either achieve other objectives that they have. But this is that simple, and it just takes a few minutes to demonstrate how that could work. Now, right after this demo, we have one more demo. And in this case, I'd like to quickly demonstrate how the new adware protection feature works in exploit prevention. As I mentioned, adware protection was added to the engine as of version 6.2.1. And basically what it does, when you try to run one of the software bundles that has adware inside, basically you execute that software right here, and we should proceed with the installation in a second. So we see it's FileZilla client of a certain version, and we click on agree to continue with the installation. And we now see that there was an adware component that was blocked. Right, it's something that exploit prevention tells us. Exploit attempt was prevented at the process with PID 2964, and that's the same process that we see in Process Explorer. So it's the process of our FileZilla client. And this component of adware was blocked, and now we can simply proceed with installation of FileZilla without any further issues. So this is quite powerful, in my opinion, to demonstrate as well, because it really solves a complex problem with a very simple method. So that was a quick demo of that, but in reality, we have a lot of examples of how exploit prevention works in the field. I hope you have seen some of these examples. Like the CCleaner example is probably the first in-field detection that we have seen, and that has happened during the beta program of exploit prevention around a year, or maybe even a little bit more than a year ago. I think it was somewhere in the end of December 2017. So basically, that's where exploit prevention has started triggering on the Avast CCleaner software. And CCleaner software is a software that is either consumer targeted or could be a commercial software. But the thing is, it's a very, very broad software install base. So it has over 2 billion downloads. If you go to Avast website, you see how many people have downloaded the software from their website. And what has happened there, it was actually an attack on the supply chain. So the Avast website got compromised and their software package was compromised. And that's something that was first discovered with mFriendpoint's exploit prevention engine during the beta. Another example that showed up recently is...
Hey, Yevgeny, before you move on, do you mind if I'd say just one word about CCleaner?
Absolutely, please go ahead.
Because I find that to be a really good story to tell to the customers. It illustrates very nicely how our tools then are in a sort of behind-the-scenes feedback loop with Talos. Because as you said, the CCleaner stuff got picked up during the sort of initial testing of the exploit prevention feature. And when they first saw it, their reaction was, oh man, it's a false positive. Right, because it was a very widely used tool, right, and exploit prevention was hitting on it. So they figured this was a false positive and they just have to sort of investigate and clean up. And then they discovered when they looked closely that no, this was actually legit malware in commonly used software. And so then they started the process of contacting the vendor and working with them with responsible disclosure the way we do. So it's a really good sort of illustration of the process that our human analysts in Talos and the telemetry that we get from all of our detections really work together.
Right. Thank you for these details, Brian. I think that's a really good story. And another part of that story is how Cisco Talos works with the vendor that had actually provided that engine to also track down other campaigns that it has detected. I think there were a few other examples recently where Cisco worked with Morphisec, who is the OEM vendor, to actually track down the campaigns where exploit prevention component triggered, and then they write, the blogs with IOCs and so on. It makes a powerful story how Cisco works with other vendors as well, not just by itself, obviously. And a few good examples here. I think the ICE-ID Trojan is an interesting one. It was spotted where there was a new evolutionary code injection technique, which is called minimalist code injection technique, which just takes 5 system calls to actually execute and inject the code into a running process. URSNIF is another one I think was spotted around a few weeks ago. So basically it was another campaign where a Microsoft Word document with a VBA macro was sent to a number of victims, and the macro had the auto open function to basically execute it automatically upon opening the document. And then the macro has been obfuscated and downloads a series of PowerShell commands, one PowerShell command downloading another one in a chain, which makes it really difficult, especially if it's all executing in memory, for a traditional antivirus product to detect it. So I highly encourage you to have a look at those in-field findings, and I'm sure that there are many, many more. I just can't fit that many on a single slide. Before we proceed, do we have any questions? Do we have anyone who has a question who would like to ask verbally?
There are a couple questions that have been asked in the Q&A panel. First one, I'll work in reverse order as they're shown to me. How do we catch the CCleaner exploit if it isn't one of the applications we don't protect with exploit prevention?
That's a great question. And I think in this specific case, I don't know the answer from the top of my head accurately. I can definitely follow up on that. I think it was targeting to exploit one another process on the protection list, which actually caused us to start thinking that it could be.
CCleaner was a vehicle, right?
The process that it's attacking, the process that it's attacking is the one that is covered by exploit prevention.
Yeah,
so it's not
CCleaner is a vehicle by which.
Yeah,
I'm sorry. Go ahead, Brian. No, you're on the. You're
yeah, CCleaner is the vector, but what we care about is that it's going after one of the Windows or commonly exploited system components that is covered by XPREV.
Right.
Yep. And then a similar question, working in reverse order here. Can we explain how the adware was stopped in the demo when FileZilla is not one of the protected applications of exploit prevention?
Right. So it also depends, with adware protection, I think we have a little bit more flexibility beyond that list of protected applications. So it doesn't have to be on the protection list for adware protection. For example, it also depends on whether we can continue the installation of FileZilla. It depends on whether this adware component is the same bundle, if it's a part of the same package of software, or if it's something that comes together with it, but not the same package itself. So with adware protection, there is a little more flexibility in terms of detection. It doesn't have to be necessarily on the protection list.
Yep. So I don't know if these slides are going to go into it. Are you going to talk about the way we actually move the application's memory space and actually stand up a phantom syscall unit there, so that if we see applications coming in trying to exploit, or did you go over that already?
Yeah, we went over that already,
okay.
quite on a high level, but that was the part.
I missed it.
No problem.
Yeah, so if you can, just kind of go over this again, right, so that it's clear for a couple people to understand, right, sure. That it's not that we are looking at system calls to the true application of Windows Word, Microsoft Word, or a browser or Adobe Reader, but we're looking at what has been stood up in its place. But if you can, just kind of go over this again for us.
Yeah, so basically the way it works, we have Windows Loader, and basically it's a small component of Microsoft Windows that is responsible for loading an application when it starts. When a user clicks on Start Application, it loads the executable itself, it loads the libraries that come together with that executable and that required to make it work. And basically, exploit prevention itself is another small library that gets injected into the Windows Loader, if it makes sense. And then when the Windows Loader starts loading that application, it actually starts randomizing the addresses of the memory of that application. So instead of assigning, the traditional address space that this application would normally get in a normal situation if it was not under protection, instead of that, it just randomizes that space, and the original space is kept as a decoy, as something that could be used for a trap. Does it make sense, or were you looking for something different?
Let's see. Let me see if I can take off mute. I don't know if I can. Doesn't appear that I can. Adrian asked that question, so just trying to see if that helps.
In a sense, exploit prevention is really setting up an in-memory honeypot, because once you've done the memory reallocation, the only things that could possibly be accessing the original space are illegitimate things.
Right.
I'm sorry, Adrian. I can't. Looks like I don't have permissions to take you off mute to see if that helps. If it doesn't, please let me know. Follow up in the Q&A panel or send me a chat message and we can get further.
Adrian, I was just able to unmute you.
Oh, cool. Thank you.
Hey, Evgeny, that's fine. Yeah, understood. Thanks.
Oh, all right. Do we have any more questions before we proceed?
Don't see any hands raised, so I think we're good.
All right. So that's where we stopped, basically on the part where we have discussed the in-field findings, and these are some really good stories to tell our customers. The next part that we have here is comparison of exploit prevention with Microsoft Emmet. And for those of you who are not familiar with Emmet, it's basically a toolkit that Microsoft provides, and until version 10, it provided as a standalone package that has a number of rules that look for known in-memory attacks. So essentially, this kind of component is trying to address the same problem space for us. And Microsoft Emmet is free of charge, so Microsoft doesn't charge anything for that. And as of version 10, it was also tightly integrated into the Windows Defender and was rebranded as Exploit Guard. So the question that we are often getting is, how is it better, or how does it compare with what AmPoint's exploit prevention provides? And here's a quick comparison that we've put together working with our OEM vendor. I think we can keep that as a reference, but on a high level, if we look at what Emmet does, it actually has an approach that is purely rule-based. So they have a number of signatures. I think in Emmet it was around 15 to 20 signatures that look for known attack patterns, looking specifically for attacks that are addressing, the memory space. And as it was incorporated into the Windows Defender, they added more rules basically. But it's still rules. You are still looking for something that an adversary can learn from. Those rules are documented. You can figure out what those rules are looking for. Like, for example, with EAF, or Export Address Table Access Filtering rule, you have a mechanism that is actually looking for shellcode that is trying to look up addresses of certain modules in the memory that could allow an attacker to execute certain API calls that are useful for downloading files, injecting into other processes, allocating memory, doing anything malicious. And what those rules are doing, like in the case of Export Address Table Filtering, they're actually looking for the shellcode that is trying to get those addresses of those modules. So if the attacker is smart enough, and if they know that the rule is looking for something specific, they can actually find a way to bypass that rule. And that's one of the fundamental differences of how Emmet works versus exploit prevention works. Exploit prevention doesn't have any signatures. It doesn't have any rules. It's fully proactive. So there is no easy way to reverse engineer on how it works or how the memory allocation works when a new application starts, because it's always random. It's always randomized. There is no way to decode this randomization or to figure out on how it was randomized. So basically, that's the big difference. I think most of this we can keep as a reference material. There are several examples of how Microsoft Emmet was bypassed successfully. By just doing a quick Google search, I'm sure that you can find many more examples of this being bypassed. So I'll keep it here for you. One another common question that we are getting asked is how can we make sure that the products are coexisting successfully together? Right, yesterday Jesse has put a lot of detail in discussing exclusions as one of the ways to make products coexist. And something similar is actually possible with exploit prevention and Emmet. Even though they're both addressing the same kind of problem space, there are certain rules in Microsoft Emmet that can be disabled to avoid any compatibility issues with XPref. So for Windows 7, it's specifically the EAF rule. For Windows 10, it's the 3 rules mentioned here, EAF, IAF, and ACG rule. So all 3 rules have incompatibilities with XPref. We have done quite a thorough testing of that, and we have also worked with the vendor to kind of confirm that their field experience and our field experience and our internal testing aligns well together. So basically, if a customer wants to run both Emmet and XPref together, they can do so. And that summarizes the exploit prevention engine in mFriendpoints. We've spent quite a bit of time on that engine, so I'd like to proceed and quickly touch on the system process protection engine, which is one of the other engines that work in memory. And frankly speaking, whenever a system gets infected or compromised, either through an exploit or any other means, one of the things that malware could potentially do is try to shut down the existing endpoint security solution. And oftentimes, what happens is that vendors start thinking, how can they implement a component to protect themselves? How can they write a component that protects their own application from being tampered with? So essentially, mFriendpoints as well has a self-protect driver, and that driver protects the process of sfc.exe from memory injections or process injections. Essentially, this was working pretty well. That's why Cisco decided to actually leverage that capability and apply it to a bunch of other system processes. And we have the system processes on the right side. One of the notable processes is lsas.exe. I think most of you are familiar with its ability to store the credentials. And there is, of course, one of the attacks or one of the tools, which is called Mimikatz, that is able to dump credentials from that process if it's not protected. And that's one of the things that we have advertised initially as what system protection can protect against. There is one more example here of a detection that we have with Windows Logon application. It was detected using one of the machine learning algorithms that we're going to discuss later on in this session. But basically, that's another attack on one of the processes on this list, right? So we have a WinLogon application where a malware has likely hollowed out a process wrapper and started using it as one of the applications for crypto mining. So I hope that makes sense. That was the summary of the in-memory engine. So we have discussed briefly the XPref and the system process protection. The next section that we have here is the on-disk protection engines. And unless we have some outstanding questions for the in-memory stuff, I'd like to pass it over to Brian to go over the set of engines working on disk. Let me pass you the ball, Brian.
Nothing in queue, no hands raised currently.
All right. Thanks, Evgeny. So that's a great start. The memory-based protections sort of cover from a theoretical standpoint, you want to think about the sort of data in process component, and on disk is extends the protection then to also the data at rest and in transit as it moves in and out of pieces of the system. So that begins with the piece that we now call MAP, malicious activity prevention. This may actually be easier to wrap your brain around if you go back to the original name that this went by on some of the roadmap engineering before this saw the light of day, and this is the sort of host-based IOC component. I'll talk in just a few minutes about the cloud-based IOCs, and those sort of have been in AMP for a good long while, and they fit the sort of general AMP for endpoints philosophy of trying to do as much work as possible in the cloud. That's how we can get a relatively lightweight endpoint connector on the client itself. So one of the things that people often note when they're evaluating AMP against one of its traditional desktop protection competitors is that it's actually, AMP is fairly parsimonious with system resources once it's installed and operating. And obviously, the initial scan is a little bit heavyweight, but most of the time, AMP tries to minimize the load placed on the client, right? You do the hash calculation on the client, but then all of the lookups on the back end happen in the cloud. And the same thing happens with IOCs, but there's a problem with the timing there. If you think about the way like ransomware works, and if you wrote an indication for ransomware behavior that has to do with like the creation of a lot of high entropy files, which is how you detect like the process of ransomware starting to encrypt your disk contents. By the time the indicator sort of makes the round trip to the cloud and back, a rather large amount of damage has already been done. So in order to tighten the detection loop for a couple of these fairly tightly focused ransomware-specific behaviors, malicious activity prevention moves some of the IOCs onto the client itself. Now the trade-off that we're making there, of course, is that that does impose more of a load on the client resources. So we want to do this judiciously, and malicious activity protection is focused on a couple of very, very high fidelity indicators that are specific to ransomware behavior. And the idea there is that we can detect the behavior and stop the process that's doing it before a lot of damage has been done. Now, some files will, by nature, get damaged in this process, right? You can't have an indicator of compromise unless the compromise has already happened. The goal here is just to tighten the detection loop by moving some of the processing to the client itself, so that the detection and the block can happen as quickly as possible in time. And that's really it. The IOCs are still getting maintained by Talos. They're still getting pushed by Cisco, but it's just that some of the processing now happens on the client itself as opposed to in the cloud. The way you turn this stuff on, and this is going to cover both the malicious activity protection that I just mentioned and then the in-memory components that Evgeny kicked us off with. You're here in the AMP policy edit, and here's where you configure a whole bunch of stuff. There was a question that came up, I think, on day one, right? That had to do with when you switch between audit mode and quarantine mode, does that cover all the engines? And here's the answer, right? It's actually configurable at a granular level. What we think of as the traditional AMP quarantine and audit mode is up there under file conviction mode. We either, based on the hash of the file, will either quarantine something or just audit the activity. Similar thing happens with the network piece with DFC, which I'll get back to in a few slides. And then highlighted here, the malicious activity protection, you've actually got multiple options. Starting from the right, you can disable it entirely. You can run it in audit-only mode, where it will just record the activity. You can have it block the action, but not quarantine the file that was the source of the problem, or the generally recommended setting here for malicious activity protection on regular endpoints is quarantine. Now notice the little blue box to the right. We've got recommended settings for workstations and for servers. The current recommendation, at least, is to turn off both the system process protection and the malicious activity prevention for servers. It's possible that that's going to evolve in the future as the comfort level increases, but that's the current recommendation. Yeah, and again, you can see with system process protection, you have a choice of protect or disabled. And the XPrev engine is just a checkbox, right? That's either on or off. There is no concept of an audit mode in exploit prevention. Any questions on the config side here? We've got, all right, not hearing any. I will proceed. So let's talk a little bit, this is something that Jesse broached in his best practices session yesterday. We spent a fair amount of time talking about the offline engine, and also we'll spend some time today refreshing our memory about the Tetra update server. So Tetra, just to recap, is our offline protection engine, and offline protection engine is how AMP spells classic antivirus, signature-based scanning for the Windows platform. This is something that on the Mac and Linux platforms is provided by ClamAV with a custom signature set, but on Windows it's Tetra, right? And then you turn that on, and then you've got it running. It is not to be confused with the advanced custom detection down there, where we talk about ClamAV style signatures. So let me try to unconfuse some of this for you. Oops, pardon my update here. The offline engine, its basic purpose in life is to provide protection to the endpoints when the endpoint is unable to contact the cloud, right? So the basic use case for the offline engine has always been, because AMP does a lot of its work in the cloud, what happens when I can't see the cloud? And the answer there has always been, well, we'll give you a sort of second line of defense that is classic host-based signature scanning, so that even if you can't talk to the cloud, you still have a chance of catching known bad stuff. Then customers say, okay, now I want to be able to block files myself. It's great that AMP will tell me when something is bad, but I want to have the ability to do custom listing myself. And the simplest way to do that is just for the customer to add the SHA-256 hash of the file to a custom list. And that's what's known as a simple custom detection. It's just a hash, and it just turns into a block event, just as if the AMP cloud had convicted the file. There's really no difference in the behavior there. It's just what is the source of the hash that I'm blocking on? Is it Cisco or is it the customer? The advanced custom detection actually lets you use the ClamAV language to write a detection rule yourself. Now, you can't use everything that's in ClamAV. The bulleted list there is an important reference. These are the pieces that ACD actually supports for these advanced detections. And one of the often overlooked use cases for this has to do with hashes, because AMP does everything with a SHA-256 hash, which is fine, right? It's state of the practice. Unfortunately, there are a lot of organizations that still provide IOCs using MD5 hashes instead of SHA-256 hashes. And there are a couple of ways around it. One is you can plug the MD5 into VirusTotal, And assuming that the sample you're looking for exists in VirusTotal, then you can derive the 256 hash from that. You can also write an advanced custom detection rule, because ClamAV lets you look for an MD5 hash. So you can write an MD5 hash for the stuff that you got from your advisory capability or whatever the source of your IOC is, and use the MD5 without having to translate it into SHA-256. This is also good for writing sort of classic signature stuff, where I'm looking for a chunk of something within a file, a byte sequence in body of the file or something like that. So if you're looking for something that has bad stuff in it, you write signature for bad stuff using ClamAV, and then that becomes an advanced custom detection rule. So that's a way of sort of doing your own customized signature scanning. And again, this is something that's going to happen on the endpoint by its nature. Now let's revisit some of the AMP server pieces here. Jesse talked about this yesterday in the context of best practices, and I'm not going to try to go over again all of what we covered there. I'd encourage you to sort of refer back to the recording from day 2 on a lot of that stuff. What we're talking about today is the configuration side of this. So I'm going to sneak through the couple of slides here that sort of recap the basics here and talking about how we're actually going to configure this in Poly. So on the offline engine, on Tetra, on Windows, on the client side policy, you can configure an update interval. That's how often the connector will check for updates to the engine's signature database. And then, this is key for the local update server, when you tick that box, you now have the ability to specify your own host FQDN for the update server. So here's where you would point clients to the local server rather than the Cisco provided cloud source of the signature updates. And because you're doing this in AMP policy, this is where you would do the stuff that we talked about yesterday, where if you have a case of a certain group that are mobile users and it's very difficult to get them back to your local update server, you'd create a policy for them that does not have local AMP update server checked, and that means that they would continue to go get the sort of over-the-air Cisco-hosted version of the signatures. For the stuff that you do want to have local, you enable this and point it at the appropriate server. You could even do like a sort of geo-based distribution. If you have, say, some hosts in North America, some hosts in Europe, some hosts in Asia, and you're concerned about bandwidth, you could actually provide a local update server in each of the locations, and then you'd need to create policies for each of those locations pointing to the appropriate domain name there. And then the last piece in the config on the client side is whether to use unencrypted HTTP or secure HTTPS to fetch the updates from the server. All right, on the server side, here's what the config looks like. You have a choice of hosting this either on a Windows server or a Linux server, and whichever one you want to do, you click the appropriate download button to pull down a little bundle that has the update server piece. You also then create a policy XML file that governs how the update server behaves. And right now, pretty much the only knob that you've got is how often the update server queries to see if the signature database has been updated, right? So in the last screen, our update interval was how often the client endpoint connector pings the update server for an update. This is how often the update server checks the big wide world to see if there's a new version of the Tetra signature database. That's pretty much the only thing there is to configure right now. Then you download the XML. And what you do from there depends on which of the deployment modes. Now big variable here is the dividing line between fetch-only mode and self-hosting mode. With fetch-only mode, the assumption is that the customer is providing a supported web server, and that will be the host for our update server, as well as whatever else they're running on that web server, right? So if they've got an Apache or if they've got an IIS server and they say, that's what we want to use as our AMP update server, then they're in fetch-only mode. What that means is that the component that we provide, the little piece of server software that you've downloaded here, all it's going to do is fetch the updates and park them in an appropriate part of the file system so that the customer-provided supported web server can then serve them out to the connectors when they call in. And the sort of the single update mode of fetch only, which is going to be you've got the web server provided by the client, and you set our update server's checking interval basically as a cron job or scheduled task, depending on your operating system of choice, and that's what then maintains the file. That is by far the easiest to deploy in the enterprise scenarios here. Periodic, again, it's the customer-provided web server, but our update utility is then handling the scheduling. In the case where the customer does not have a web server that they're going to provide for this, then we switch to self-hosting mode, and basically what that means is that we provide a little web server ourselves. As part of the package here that you download, that does also include a bundled web server like Nginx. And in the self-hosting mode, you turn that on, and then our server is running to answer the web requests. Now, note that means that our server software needs to be able to bind to the well-known privileged ports 80 and 443 to receive the incoming requests. Also notice that means that you don't want to run a self-hosting mode AMP update server on a system that does also have a parallel web server existing itself. Why? Because they're going to run into a conflict if they both try to bind to the same ports. So the self-hosting mode is really intended for a quick stand-up for a proof of concept, or a small deployment, or a lab, or something like that, where you don't already have a web server infrastructure in place. Does all of that make sense, or have I just added hopeless confusion?
Well, don't see any hands raised.
All right, so I have stunned them into silence. That's fantastic. We'll power on. So this is going to be for reference. I'm not going to sort of drain all this here because the slides will be provided and the recording will be provided, and you can just use this as a reference. So here's what happens with Apache or Nginx. on the update server side. You give it a place to live. You want to pack this stuff and set the policy up. And then the way you test it is you browse first on the file system, check to make sure that the signatures are coming in the file system. Then you check again at the next sync cycle to make sure that the updates are happening. That's verifying on the server side. And then, of course, you make sure that the clients are going in the console as properly up to date. Now, in this FAQ, which again is mostly a sort of for your reference thing, let me draw your attention to the second Q&A item there, and that's a link to that document, AMP Tetra on-premise server configuration, and that has a lot of info on standing this up and configuring it. I see Tim has a hand up there. Can somebody unmute Tim, please?
Hey, Brian, it seems like if you have the ball, you can unmute him, but not the other person.
Hey, okay, well, in that case, let me try.
I cannot, yeah.
Where's Tim? Okay, there's Tim. All right, Tim, you're live. Go.
Awesome. Hey, question about the Tetra update server. Is this our kind of go forward request to customers or recommendation to customers going forward for pretty much all cases now in not using the cloud? And the reason I ask is that for every POV I think I've done for the past year or so since we introduced the deployment summary and the Tetra definition status, every single customer has definitions outdated, and it is a source of contention for every single customer that does a POV because they can't get it out of their mind that their Tetra definitions are out of date. So I guess kind of a larger question or two-part question. One is, seems like we have an issue if they're updating via the cloud for Tetra. And then the question is, do we recommend then people do this for everything?
So if you have a large batch of physical workstations that are non-mobile, then absolutely the update server is your best bet. It's going to provide you on-site access and make sure that everything's up to date as quickly as possible. If you're using a lot of roaming users, then that's not the use case for that. In terms of the definition of files being out of date, the reality is that the reason that those show out of date is because our update window is set to 1 hour. So as soon as an hour goes by and they haven't pulled a new def file, it shows out of date. I personally feel that that is a little aggressive. I think that a 4-hour window is far more realistic, but that's not my decision to make in terms of how the defaults are set.
Right, and I think the signature set updates every 20 minutes or so. We can actually see the latest signature set on AMP tools. I'll share a link in a second.
You can also get the latest signature number from the computers page. Any system that has Tetra enabled, just hover over the definition number and it'll give you the most recent version number right there.
Yeah, I've just basically relegated to having them set it to 24 hours so they never see it because it's a massive issue for customers they can't get over. So.
Right. Okay. And yeah, I wish that there were an easier way to ease that pain. It's something we've been fighting with, and I don't quite understand the reasoning and logic behind having it set to 1 hour. I think 4 hours is a perfectly rational window there, but yeah, I don't make those decisions, so.
No sweat. Thanks for the answers, guys.
In my experience, the way you fix problems like that is you have the developers take a couple of tech support calls, but, you know, that's just me. All right, are we good to go there? Thanks for the question, Tim. And if you don't mind, could you pull your hand back down because WebEx doesn't do that automatically. Thanks.
There's a couple of questions in the chat regarding the Tetra server. George or Jorge? Probably Jorge.
Jorge, yeah.
All right. Is there any integrity verification on the pattern files in the update server? I'm going to have to say yes, there is, but I couldn't tell you how it works. I simply don't know. Do you guys?
Don't know how it works. I'm sure
that.
there is. Right. So if we peel back the Band-Aid for a moment, most of you probably remember our issue with the bad deaths file or DAT file that we got from the Tetra vendor a few months ago. And so in response to that, there have been checks put in place on multiple sides for us to, one, do integrity checks, some other verification, things of that nature on what we get from the vendor. Understand that for Tetra, we don't write those definition files. We get those from the vendor that gives us the Tetra engine. And so there is now some further check and verification that happens because of the black eye we received as a cascade of getting a bad deaths file from our vendor. So the answer to the question is yes, there is. The level of integrity verification is something that we have to go get details for and bring back to you if it's something that's, if it's an answer that's needed. And if that is an answer that's needed, feel free to reach out to us on the team mailer, and we'll bring that response back with the level of detail that will help either answer the question for you or for a customer who may be asking.
I think that that's a really good point, and I think you hit on another important point there, which is that we're getting those definitions from a third-party vendor, and then we have to populate our update servers in the cloud with those updates as well, which adds increased latency and time to get those definitions down to the endpoints when hosting them from the cloud. So looking at all the jumps in place, I think that explains why we're seeing a lot of latency issues there.
Yeah, I'd agree with you, Jesse. We probably need to, if it's not already built, consider at least an FMR on getting that time window from an hour to 4 hours, just something that makes the product, that doesn't raise unnecessary questions in the customer's eyes, right? So that whole issue of outdated deaths is something that we can avoid with just a small change in the default settings on update time and what shows in the console. Ibrahim, you had a question around the update.
Yeah, let me unmute Ibrahim if I can find my mouse pointer here. There we go. Ibrahim, you're live. Go ahead.
Yeah, great. Yeah, it's related to what you guys had said earlier with regard to the Tetra engine being my understanding is the client calls for a query whether the update cache has changed, and the console confirms that. So the endpoint shouldn't really make a decision. If you are saying after 1 hour or 4 hours, it gets stamped as being out of date, who's making a decision to actually report onto the console there is now a machine that is out of date? I think it's important that I understand that, because the way I was brought up, if I put it that way, was actually exactly how I explained it. The console should make the decision, and the client should have some sort of a way of keeping onto a timestamp unless it's changed. And if that has changed, when it compares, then it downloads something, and then it queries and says, yeah, now you are out of date. Maybe I've got the wrong end of the stick. Can we go over that again once more, please?
I'm sorry, I don't think I got the gist of the question. There was a lot of overriding humming and background noise. But it sounds like you were talking about some of the oddities in showing an outdated connector and where that decision gets made between the connector information and what the console has for check-ins. Is that what was I hearing? Am I hearing properly?
Yeah, that's right. When we see, I can't remember the name of the gentleman who raised this point, but I think it's an important point. Once we see the Tetra engine is out of date, can someone walk me through how that decision is made? I think I can simplify as much as that.
Yeah. So where the decision is made to mark it as out of date in the console, is that what you're getting at?
Yes, Eric.
Okay, got it. So unfortunately, I don't have the details on the logic as to what goes into saying out of date. That's something I'd have to go to engineering to get. I just have not ever asked them the specifics of that logic. I do think it's something that we need to tweak based upon both what I've seen in my own, console setup and what I've heard from customers, but I don't have the details of the logic. Let me take it back and let me and the team take it back as a point to investigate, if you would.
Yeah, thank you.
Okay. To your other question, Ibrahim, about not serving up clam defs. So it's a two-pronged issue, and one of them is not really an issue, right? So ClamAV, when it comes to Windows systems, is the only thing there that is used on Windows connectors is a small ClamAV library. So Tetra on Windows is not ClamAV. And so if there were any questions, I want to make that clear to everyone. Tetra on Windows is not ClamAV. Tetra on Windows is a antivirus vendor from which we OEM an engine and pull it into the connector for install. And so we don't need to serve up any ClamAV signatures for Windows systems because there are no ClamAV SIGs used in the offline mode or antivirus mode. The ClamAV library present on a window or within a Windows connector install is for the front end file typing, file identification, things of that nature. And if we were to do some advanced custom detections, there has to be something to decode the ClamAV SIGs that are written in the console and then use that locally on the on that host. So that's where ClamAV comes to play in the Windows connector world. Linux and Mac, that's an entirely different story. Offline there is ClamAV. The local Tetra update server was designed, one, to meet a compliance need, if you will. And so there was some timing that was done. If I remember correctly, and I'm reaching back a couple of years at this point now, this may have even been connected to the work we did around PCI DSS and having a QSA come in and vet AMP for endpoints in those types of environments, that we needed to have some local update server available in order to be able to check the boxes if used in such an environment. And then that gave us what we would call a minimum viable product, right? What's the basis that we need to do to make this work, and how quickly can we get that done? It was easier because we already have structure around serving up definitions for Tetra and the OEM that we source that engine from. We already have that structure in place, as Jesse mentioned a moment ago, where we get their updates and their signatures, we put them and post them on our Tetra definition servers within the .cisco.amp.cisco.com domain, and then make it available to everyone else or any other connectors that need to come and get that. So that infrastructure was already built, understood, and in place. CLAM signatures are a wholly different thing, and it did not meet timelines. It did not meet the minimum viable product need. It did not meet we were not going to be able to get it done to meet the requirements for which the local Tetra update server was needed. Now, that said, we have asked many times, and we do think we're going to get it, where the local Tetra update server can serve up CLAM SIGs, but there's work to be done. It's not currently on the roadmap with any release date, but we do think it's something we can get done, and we're continuing to ask PM to push to get it on the roadmap. If you have that as a feature request, please, let's get it, and let's put it in, and let's add weight to it so that it raises up in importance when PM comes to go and vet FMRs or feature requests from the field.
In fact, a big part of the reason why the software changed its name from Tetra Local Update Server to AMP Update Server was because of this recognition that once we've created this thing, it could be used other local staging tasks as well. And so that has always sort of been in mind. It's just a question of how long does it take the features to get prioritized versus the really long laundry list of other things that they have to work on.
Yep. Ibrahim, hopefully that addressed that ClamAV specific question you had.
Oh, yeah, no, thank you, Eric.
Okay, and we're going to take back the other item, and we're going to investigate that on troubleshooting out-of-date status on connectors and where that logic lies. And we'll ask engineering whether it's something that needs, if they can tweak it in any way after we kind of give you guys feedback on it. Brandon Rosiak had a question. Let's see. Has there been any consideration on allowing a customer to elect an AMP connector to be a Tetra update server to allow the copy of the Tetra folder with definitions to other connectors without having to go through the Tetra update server configuration? So one system gets it, one known connector in the environment gets it, and then turns around and serves that up or makes it available through some sort of secure comms connector to connector. And the short answer is no. This has been something bandied about for other things, right? Can we allow the connectors to talk for other reasons, other purposes? You know, in an incident response mode, we may want to have something that allows connectors to join together and build in, you know, I don't know, memory dumps or something and ship them all up at one time. There have been other reasons that these types of apps have been set before engineering, and they are very, very slow to build in, and my WebEx just crashed. I'll be back in a moment. But engineering has been very, very slow to build in shells of any sort inside of the connector that allows for other systems to come in and manipulate a host, even if it's just reading data from that host, because of what that opens up.
So I know we discussed that when I was in support. We talked to Dev about that a couple of times, primarily because we've seen that in other security products, right? But the answer we got was uniformly, we're not taking that approach with it for a couple of reasons, one of which is we don't want to bloat the connector code base or resource utilization on all the endpoints, just so that we can, on the fly, designate one of them to handle updates. And yeah, there's some cool stuff you can do with that kind of functionality, but again, as Eric said, it opens up a lot of cans of worms that are potentially dangerous, and so it was decided it just wasn't a very good feasible option in terms of centralized management and moving forward.
Hey guys, the reason you want to do that is for branch offices that may not have servers. Trend Micro has been doing that for years, and they have a special agent for the machine that's at that branch. So you don't really update the code for all of the endpoints. You only do it basically a special connector, a special agent for one host at a branch to do all the updates to it. Otherwise, you're using a lot of backhauling across WAN connections that don't have the same speed as or internet bandwidth sometimes as you know, your local area. So that's kind of what the need is. I assume, Rosiak, if that's, you know, correct me if I'm wrong, but that's what I've seen in the past. McAfee kind of has a way to do it, but probably one of the best ones I've seen is the way that Trend Micro actually does it.
And I understand that, and I agree to a certain extent that reducing that backhaul bandwidth is always an optimal decision where it's possible. But by the same token, we're talking about a few kilobits of data every hour. So the bandwidth overhead requirements are so minimal to begin with that it's almost hard to justify that kind of engineering investment.
I mean, I would agree unless you're talking about like a Tetra update, right? I mean, if you're talking Tetra updates, those are going to come down as a chunk.
Even so, the Tetra update is still very small in general. The initial package install is large. Beyond that, the updates themselves are relatively tiny.
Yeah, having, you know, oil and gas and financial both, those networks are extremely latent sensitive and don't have a lot of bandwidth in general. So that's, you know, That's why it's key in certain areas. I mean, it really is a limit of the bandwidth they have, despite how little we think it takes. It's a lot when you add it all together. So probably something we need to definitely, address. Because this is, I mean, it comes up on a regular basis.
Well, if that's the case, by all means, let's get a feature request in and get the discussion going with development. I can't promise anything, of course, but maybe they will reevaluate their previous decisions. I'm perfectly happy to have that discussion again. So.
Yep. Thank you.
Question from Torsten in the queue. After which time period the endpoint is offline for X days? Yeah, that question came up on one of the earlier days, and I don't know that we have the answer yet. Does anybody know what the sort of timer for Tetra for a complete refresh of the SIGs is versus an incremental?
I don't know. That's something we're going to have to find out.
So that's still on our homework list. Sorry. If I haven't missed any raised hands or questions, then there's one last thing that I want to say here, and it's the very last item on this FAQ. This is just something important to keep in mind, that there's no fallback logic currently, like, if it can't contact the local server, then it'll fall back to the cloud or something like that. People have certainly talked about things like that, and you mentioned it would be really cool if you could add like a kind of like what AnyConnect does for some of its modules, where you can have one behavior if you're on the trusted network and another if you're mobile. But none of that is currently in any of the bits. That's all sort of on that very long wish list. Are we ready to roll on? Sounds like we're good.
I think so. Should be good.
So my next task is to step us through the couple of post-compromise items here. The first of which I've already sort of broached when I was talking about the on-host component of this, right, what we call MAP, the malicious activity version. The cloud-delivered IOCs have been in the product a lot longer than that, and these are things that come from Cisco that are actively maintained by Talos to stay on top of currently seen behaviors and exploits and things like that. They also, of course, make avid use of new features in the connectors as they are added. And the favorite example that I always use there is when command line visibility, the ability to collect command line arguments and things like that on the connector first got added, then the Talos folks avidly jumped on that and started providing cloud IOCs for the stuff that they could now detect as well. So that's something that happens in the background and transparently to the customers, but it's going to show up as these sort of cloud IOC detections. Then there's, again, the ability for the customers to roll their own. And a customer can actually create a sort of customized endpoint IOC. Unfortunately, using yet another way of describing it, so the endpoint IOC feature for historical reasons that predate at least one acquisition, if not two, used the OpenIOC format, which is maybe a slightly unfortunate choice because, as you may know, that OpenIOC was originally produced by Mandiant, which is now FireEye. But they have sort of set this free. It is its own thing now, and it is a very powerful way of building a sort of custom crafted indicator search on the endpoints. And it is, I think, it's generally an underutilized feature, and there may be some perfectly legitimate reasons for that. One is because you have to learn how to write an OpenIOC formatted rule if you don't have a sort of provider who's doing that for you. And the other is that this is a sort of triggered event that can be quite resource intensive on the endpoint, especially the first time it runs, because the first time this stuff kicks off, there's actually a sort of cataloging process of the endpoint that takes place that can be quite long in duration and impactful on the host. But it's very powerful in terms of what you can actually look for. So it's really something that you want to keep in mind primarily for sort of threat hunting or active incident response scenarios where you're looking for something very specific and you want to know if a particular indicator or artifact is present on the hosts that you're looking at. And again, you'd probably want to do this for a carefully constrained group of hosts, not enterprise-wide, because of the load that it imposes. Another sort of post-compromise detection option is the network activity itself. Whoops, hang on, Torsten has his hand up. Let me find my unmute option here. Torsten, you are live.
Perfect, so can you hear me?
Yes.
Can you hear me?
Yes,
perfect.
Go ahead.
Right, just one question. Do we have any information regarding real-time IOC on the endpoint?
Real-time IOCs? I think the answer is not yet.
Yes. Any info, because I think it's a really great new feature which will come up, and just curious if you have new info about that.
Are you referring to the live search? What used to be called endpoint search?
No. So in Calgary, we talked. The development talked with us what they're planning, what they're thinking, and there was one thing like the endpoint IOC. So that means if you upload an IOC, it works like a signature on the endpoint. But real-time IOC, I don't know if it is. Maybe it's. I think it's not the real-time search.
What you have described with this really reminds me of the advanced custom detections where you create your own IOC, which is on the endpoint. But we can have an offline discussion on this.
Yeah, okay, it does sound a lot like ACD to me too, but it's possible that they've got something else in mind. So I'm curious. Just a couple of quick notes about the DFC, the device flow correlation feature. This is something that will provide an indicator based on like a callback from an initial stage that made its way onto the endpoint that is now trying to download the next stage of the attack or something like that. And it primarily is based on, again, Talos maintained list of known command and control channels, hosts that are known to distribute badware and things like that. Customers can create their own, both whitelist and blacklist by IP only, right? So everything that DFC does is based on IP addresses, not URLs or domain names. And while that sounds very old-fashioned, you know, the old stuff is in fact still around. I mean, when I had the threat wall live in Barcelona a couple of weeks ago, we got on the FMC, we got a hit on a very active crypto miner that was walking around the show that was using hard-coded IPs. And the reason we know that is because they showed up on our screen at all. Right, because everything that was using domains was getting blocked by Umbrella before we could ever see it on the threat wall. but this one old school tool was using IP addresses, not domains. Therefore, there was nothing for Umbrella to block. Therefore, we caught it the old-fashioned way with the Talos threat intelligence and the IP list. So just because it's old doesn't mean it's not relevant anymore. And that, I think, might be everything I have to say about DFC, unless there are follow-up questions here, and there often are. All right, well, we can catch them in the Q&A later if there's something hanging out. ThreatGrid, the ThreatGrid integration has been a flagship feature in AMP for a good long while. It is very powerful. It demos well. I do want to take care to echo what Doak pointed out on day one here, namely that there has been this historical tendency to think that ThreatGrid is the source of detections for AMP, and that is nowhere near the case, right? ThreatGrid provides behavioral indicators, not definitive convictions. And the source of truth for whether something is bad or not is going to be the AMP disposition, not a number that you get from a ThreatGrid run. So that's always very important to keep in mind. Having said that, having all this capability built in here and available in the AMP console has always been a really cool thing to show off, and you get a lot of power under the hood that way that customers can use. The most common way I think that this gets referenced in AMP for endpoints is using our low prevalence logic here. Now, this stuff does need to be turned on in policy group by group. But the low prevalence logic is based on the idea that it's the weird stuff in your environment that is of the most interest. And uncommon executables, now PE, Windows only, right? Because that's pretty much all you've got a chance to get anything back from ThreatGrid right now. But if you have unusual, not commonly seen files that show up on one or two endpoints, you can then use the low prevalence logic, if you enable that, to then automatically submit those oddball files to ThreatGrid for analysis. Reasons why this is not turned on by default include that we don't want people to unexpectedly burn up their entire ThreatGrid quota before they know it. Also because there are privacy implications, right? So you want this to be a deliberate decision that a customer makes, that they are going to send stuff from their environment into a sandbox. And depending on your geolocation and your privacy regime, that could be a very different conversation depending on where you are. I always like to tell people that I know how to pronounce Bundesdatenschutzgesetz. Privacy-sensitive environments you want to sort of support by default. Having said that, it has been, I think, a really good source of hits for us. It's a way of using our AMP installed base to find oddballs and get them into ThreatGrid, and therefore also in front of the eyes of the good folks on the Talos team when something new does show up. And we've got the privacy data sheet links down there in the lower right-hand corner for your reference. Anything about this? I think it's fairly familiar for a lot of folks on the call, but let me just pause for another minute and see if there's a follow-up here.
Bill Yazzie has his hand raised, or had a question. I don't know if we didn't get it covered or not.
Bill.
He's got a question mark near his name, so.
Yeah, so that means that he's got a question in the panel, I think.
Okay, let me look if I can find
Q&A.
Maybe there was a comment rather than a question, I think.
Oh, okay, yeah, I see it. It was a comment. Yeah. I see you, Bill. I'll take that as we kind of dig into this console thing. I see it. Thank you.
All righty. Thank you for that. To recap and summarize, here's the sort of world of online and offline engines specific to the Windows connector here. Right, so when you are connected to the cloud, you have all these wonderful things. You've got the AMP cloud for disposition lookups, right? Good, bad, unknown. You've got the cloud-based IOCs that are active. You've got customer-written endpoint IOCs that could be delivered there. You have access to Threat Grid and the simple custom detections. Now note, you might think, well, simple custom detections are locally defined, therefore they're available offline. Not so. The hashes for the simple custom detections are stored in the cloud, just like the Cisco provided ones. When you are disconnected from the cloud, what you've got is the exploit prevention engine, if it's enabled, system process protection and malicious activity protection, if enabled, your offline engine with Tetra and your AV signatures, and then advanced custom detections, which do get pushed to the connector as a rule set. And therefore, ACDs, unlike the simple custom detections, are active even if you're off the grid. And so that's a sort of lovely summary of what needs to talk to your public or private AMP cloud resources and what doesn't. And then also a sort of quick little reference, here are the engines and protection mechanisms platform by platform. So basically everything has some level of a hash-based reputation lookup. On the Windows side, you've got a lot of stuff that is specific to PE Windows formatted executables like Ethos and Spiro, the exploit prevention pieces. All of the in-memory stuff that Evgeny went over is pretty much, I think all of that right now is specific to Windows, the Tetra engine. On the Mac and Linux side, it's mainly the combination of the hash-based reputation and ClamAV, plus things like your ACDs and simple custom detections. Network behavior exists, and the Windows-specific components, obviously, he said with a certain trepidation, don't apply there. I did notice that there was an interesting news report this week of some malware that was actually using a Mac OS Windows executable. I think it was Mono instead of Wine in that case, but they were using one of these sort of Windows executable wrappers to basically stage the dropper onto a Mac OS system. So that's going to be something we want to keep our eye on in the future. For completeness, we'll note that on the Android side, it's pretty much a reputation check at install time only. And on the iOS Clarity side, then you have the app lookups, device and app trajectory pieces, and then some enforcement that is possible there as well. And now it's time for me to hand it back over to Evgeny to wrap things up here. Let me pass the ball back to you. And off we go.
Perfect. Thank you very much, Brian. Let me just share my PowerPoint quickly. I have one more comment on this slide, and basically that's around Ethos and Spiro. We didn't cover or go through those in any level of detail today. And I think the reason here is that we want to cover some of the new machine learning stuff that we have that contributes to AMP endpoints from the perspective and gets much more attention today as compared to Ethos and Spiro. So that will be a separate part that we'll go through. And now trying to put everything together that we have discussed, all of the engines on the in-memory side, on disk side, and post-compromise side, into a single day in the life of malware story. So in that story, I try to explain the sequence in which the checks are performed by the endpoint connector. I think that's a question that came up quite frequently, so we decided to address it in this presentation as well, and hopefully help you put everything together in your head. So here we have our endpoint. We have the AMP connector cache, which caches some of the disposition responses from the AMP cloud. We obviously have the AMP cloud itself that serves dispositions to the endpoint. We have the AMP console, which is the front end of the AMP cloud, if you will. And finally, we have the threadgood, which is our file analysis service. So whenever we have an exploitation attempt, first thing that looks at this is the exploit prevention engine. And that's basically the first thing that can prevent an exploitation on the endpoint itself. If it didn't work for whichever reason, we have one of the follow-up components here, which is our system process protection. And in this case, if an attacker is trying to dump credentials from the LSAS process, that's where we can stop them. And that's basically being reported to the AMP console from the AMP connector itself. Finally, if they were successful and if they have injected themselves into a system process or simply another process, what they could do next is they could actually connect to their command control server. And in this case, we could be doing a lookup on their connection. Essentially, we are taking the IP and port pair and we are checking those against the connector cache. So there is an nfm.cache file on the Windows connector that is being used for that. And the cache would be only there in case this particular combination of an IP and port pair was already looked up. Finally, if it's not there, we go to the AMP cloud, ask the AMP cloud whether it knows or has the reputation for that pair. And it also checks at this point whether we have a custom IP whitelist or a custom IP blacklist that is assigned by this particular customer with this business identifier. One another thing that is important to consider here is that the component, the network component that is actually tracking those connections, it shouldn't be confused with a firewall. It's not a firewall on the endpoint. It doesn't block all of your, it doesn't block all of your communications. You cannot program it as a firewall. Instead, when you are trying to specify a custom IP blacklist, you can just specify an IP address or an IP address range. So it's way more basic. And also it doesn't track all of the connections. It tracks a limited number of connections per process. Finally, the disposition comes back to the endpoint, and based on that, the connection is permitted or denied, as we see here. What could happen then is if the connection was successful, and if as a result of that connection a file was dropped on the disk, we check the hash of that file against the AMP connector cache again. And if the cache is not saying us anything useful, or if it's simply not there, we go to the AMP cloud, and that's where we actually calculate two queries. The first one is the SHA-256 query, and then there is a query that sends the Spiro and the Ethos hashes to the AMP cloud, or the fingerprints to be more precise. Once it reaches the AMP cloud, if the hash is unknown, it also checks for the simple custom detections or the application blocking and whitelisting rules assigned by the AMP console administrator to actually return that back to the endpoint and enforce an action if needed. At the same time, the AMP connector cache gets updated from the AMP cloud with a new disposition. Pretty much in parallel, there is a check that is being done by Tetra or by the offline engine, and it's checking both the Tetra signature set and the signature set built through advanced custom detections. Everything is being logged to the AMP endpoints console for the device trajectory and event logs. Finally, if that file is considered to be a file that has low prevalence across the global install base, around less than 10 systems that have observed a particular executable, that executable could be requested by the AMP console automatically to be uploaded if configured to do so. So there is a low prevalence feature which allows files to be automatically uploaded to the AMP console from where they get uploaded to ThreadGrid. obviously ThreadGrid executes the file in the sandbox environment, returns back a thread score, and the mCloud based on that can update the disposition. So whether a thread score is 95 or above, the disposition will change to malicious. Whether it's less than 95, the disposition would oftentimes stay unknown, unless there is some manual process being done on particular file to actually move it towards the malicious disposition. The mConsole administrator can also see the analysis report of that file. While that's all happening, all of the behaviors or all of the actions by a particular file or an executable are being monitored by the AMP connector itself. And that's where, if a certain telemetry has indicated that there is a suspicious behavior, like in this case, word opening PowerShell, a Cloud IOC alert could be logged in the AMP console. It's important to remember that cloud indicators of compromise are not real-time. They're near real-time, basically, which means that if you have an indicator or if you have certain telemetry indicating suspicious behaviors, it's going to trigger, after the queue has gone through. So it essentially depends on the backend, on how heavy load we have at that point on our backend. But usually, from my experience, it's executing pretty quickly. The alert shows up right away. Finally, if we have a process that is executing a specific set of activities like reading, writing, renaming, deleting files on a disk of a system with rapid succession, that's where our malicious activity protection engine can take place. And that engine itself, whether it identifies a certain file as ransomware, it first sends a hash lookup to the AMP Cloud, which performs the guardrails check to ensure that we are not blocking any clean or legitimate applications, like applications performing, something like archiving. Basically, it does it 3 times, and if in 3 times, it's not available, if the AMP Cloud is not available, it's still going to terminate the process. And then, of course, there is a flow which represents the heartbeat itself, and the heartbeat is something that the connector establishes to a cloud on a regular basis to ensure that it receives the job spec. And that could be either a retrospective update or a file restore event or a new policy update. All of those are being applied by the connector based on this heartbeat. And that's as much detail as I could put on a single slide. Obviously, that doesn't go into the very details, but hopefully that helps you build that picture of how these engines work together on a single AMP connector for Windows. What we have next is the machine learning role. In endpoint security, we only have 10 minutes left, so we are not going to try to condense that entire section in 10 minutes. Instead, what we're going to do is we're going to postpone it for the next deep dive session to ensure that we are giving proper attention to that important topic. And with that, I'd like to see if we have any questions. I think it's the right time to ask them verbally, and I think we have Ibrahim with a question. Let me try to unmute you. All right, Ibrahim.
Yeah, I can do it myself, I think. I think once you do the first time, then you can do it. Yeah, the question is on your diagram on the previous slide. Obviously, we have multiple engines sometimes overlapping each other in terms of actions.
Right.
And I did come across when something is actually dealt with before another engine was able to actually determine what was about that it picked up. An error is left behind, which says, the file has not been found. I can't remember the exact error, but it runs to the same thing normally you face when you put a USB on a machine and something is picked up, and before the engine is able to clean it or deal with it, you've removed the USB. Then it's left in a sort of a state where it's hanging. And I did see a number of errors. Is there any way we can actually sort of let the system know what the right hand is doing while the left hand is dealing with the issue, so to speak, so that we can actually leave an error behind where people are left behind, whether this was actually dealt with it correctly or not.
Understood. I think that's a valid point when you have a user on one side and you have a security person on another side, and you cannot always determine what has happened with that particular file. I don't have a good answer to that question right now. If you have the details of that specific case that you have meant, I would appreciate if you forward them to me, and I'd like to dig into this a little further.
Yeah, sure. I'll capture the whole scenario once I'm able to reproduce it. Yeah.
Perfect.
Okay.
Yeah. And let's sync up on this.
Yeah, sure. Thanks.
And see if we can log a feature request or something. I don't see any raised hands. Do we have any more questions? If you have one,
I'm not
raise
seeing
your hand.
any in the. They're not seeing in the Q&A panel either. So. Okay, going once. Folks, thanks again for tuning in today. Appreciate the time spent. Hopefully the last couple of hours have been useful to you, and you've gathered some good content and some talking points and ideas that would help you as you present to customers, have conversations with partners, etc. We're going at it again next week. So Tuesday, Wednesday, and Thursday, 10 a.m. Eastern time is the kickoff. Eastern U.S. time zone is the kickoff. And we've got some good content. Next week, we'll pivot. We'll finish out this presentation piece. So we'll get into the machine learning work that's being done and how that aids in detection, what it brings to things, like the endpoint specifically. We'll take a dive into that. But then next week, we'll spend some time digging in on the Threat Grid side, talking about Threat Grid Cloud, appliance, some integration stuff there. We'll spend some time digging into, at a very good level, CTR and some of the technologies that enable it to work the way it does, right? How single sign-on works, where data lives, how the data flows happen, things of that nature. And then that last day of next week, Thursday, we'll spend some time going through some incident response and threat hunting use cases that should enable you to tell some good stories when you're talking to customers. Again, all of these sessions are recorded, and so we'll make sure you have all the links from this week. And then as we clear next week, we'll make sure you have those links also. Again, time is appreciated. Thanks to presenters. Thanks for you, attendees, panelists, everyone that helped and helped make these sessions as good as they were. Appreciate it. Thank you.
Thanks to everyone for joining your evening or morning.